Welcome to this pop-up session of Shadow the Scientist. My name is Jamika Marshall. I am the programs manager for the Shadow the Scientist initiative. Shadow the Scientist is brought to you by an incredible team at the University of California, Santa Cruz, and we are funded through a generous grant from the Heising Simons Foundation. Now, in this pop-up session, we are joined by a very special science guest, Pranvera Hyseni, who is a PhD student at the University of California, Santa Cruz, doing research in planetary science, in particular, the study of meteorites. So we will be joining her in her lab today for a tour and a look at her research. Welcome, Pranvera. Thank you for joining us.
Yeah, it's my pleasure. Thank you for having me. I think this is my first Shadow the Scientist appearance, and I'm very excited.
Excellent. We're thrilled to have you and to virtually join you in your lab. Now, this is your lab is located on the UCSC main campus, correct?
Yeah, this is the Cosmochemistry Lab in the Department of Earth and Planetary Science at UC Santa Cruz. I have been a student here for 6 years now. I completed my master's and now I am completing my PhD. I work with Dr. Miriam Tellis, and this is mostly where we conduct our experiments, where we prepare our samples. And it's really, really exciting to work with extraterrestrial material. So it's a very special place. This is one of the rooms. We have another lab, which is another different room down the hall. That's where we keep some other equipment. But yeah, it's such a joy to be here and have the opportunity to actually conduct my research here.
Oh, that's fantastic, fantastic. So, before we dive into the tour of your lab and learning more about your research, could you just, for the audience, give us some definitions here? So we have meteoroid, and meteorite, which kind of refers to the same thing, but in different locations in space, in the atmosphere, and the ground. Clarify that for us, please, Pranvera.
Yeah, so meteorites are basically pieces, fragments of asteroids that are actually falling onto Earth. So when a chunk of asteroid, a smaller chunk, we call it a meteor, it's actually coming towards, that's what it's called, a meteor. So it's entering the atmosphere, and the moment that it's not completely burned in the atmosphere because it's going so fast, and because of the friction, it can actually dissolve or like burn up completely in the atmosphere. But if it's a little larger, then it can actually reach all the way to the ground. So we call that a meteorite. And we have about 40 tons of material that hit Earth every single day. Not everything makes it all the way to the surface, but whatever makes it down, if it's not in the ocean or if it's a witnessed fall, we have scientists who actually go out there, and not just scientists, they can be also like just a hobbyist who go out there and they actually hunt for these pieces. Um, and they find a lot of them. We have different types of meteorites because we also have to keep in mind not all the asteroids in the solar system are the same. So we have asteroids that are metallic, we have those that are carbonaceous, we have those who are like hydrated. So depending where the meteorite is coming from, it's also going to look very different. So I to study all the meteorites is impossible. So in my research, I actually use a very specific group that we call carbonaceous meteorites. It's very dark material that has been um, altered by water over time. And then we have all these hydration features and hydrated minerals that have been formed in these meteorites. And that's how we know that they have been altered by water at some point in time. And it's very, very exciting to be able to work with this type of material because It's like you're using this time capsule that has been frozen in time, and it's preserving some of the oldest material in the solar system. And you can use that to study and to investigate and learn about the evolution of the solar system. Like what happened, how did this form, what temperatures, how far away from the sun. And that's basically what we do here in the lab. And it's quite a privilege to be kind of like a cosmic detective or something like that.
Yes, yes, definitely a cosmic detective, a cosmic forensic,
I
uh,
know, right?
forensic
Forensic
scientist.
scientist. Yeah.
Yes, absolutely. That is exciting. So, where do most meteorites get discovered? And why are these locations, why do they tend to be ideal for finding meteorites? And I know one place is, of course, Antarctica, and in places where we have lots of snow permanently because these dark carbonaceous meteorites stand out in the snow.
That's true. Meteorites fall all over Earth. Like there isn't like a preference where they fall, like whether it's poles or the equator. But also, yes, it does have to do with how easy it is to find them and to have access. Because if something falls in the tropics, good luck finding it. There's like no way you can find it. And also, a lot of these meteorites, if it's carbonaceous, it's also very fine-grained, fragile material. So if something like this falls, let's say somewhere in Europe, for instance, or like a heavy humidity area, like a tropic area, it will not last very long. It will be dissolved like probably within months. It's very, very fragile material. If it's an iron meteorite, then that's a different story. But to be able to find these, usually scientists go to deserted areas or very cold areas that are very dry and the weather is not going to impact them. So and Antarctica is like very good location. And NASA has programs where they actually get a team of scientists and they go out there and they spend months looking for meteorites. And those are some very pristine materials. So the Antarctica ones, they get basically collected. They have not been weathered. They have not been rained at. They have been very little contaminated by like Earth's environment. And when they find them, they're very careful on how they kind of pack them up and how they handle them. So those are some very, very special samples. And usually whatever it's found out there, it belongs to the US government. So as a private collector, you cannot collect Antarctica meteorites. I don't know if you knew that. But there are other people who go like in the Sahara Desert, like Northwest Africa is actually very known for a lot of meteorites because
Yeah.
again, being out there in the desert, it's just easy to look around to get like a magnet or something like metallic detectors and just kind of go around and spend days hunting for space material. And then there are like some features that you can kind of keep an eye like whether the if you find something and you're not sure whether it's an earth rock, you can look whether it has a fusion crust or is it heavy, is it magnetic, like some overall like textures. But to be able to tell what kind exactly, then you would have to get it in the lab and use an SEM, like a scanning electron microscope, to look at the composition. And then based on that, you can actually tell what type of meteorite, whether it came from an asteroid, whether it came from Mars or the moon, any of that. But yeah, we Northwest Africa is very much known. Antarctica, Australia, Southwest United States, the deserted area. There are a lot of groups that go hunting. I went one time near the Arizona crater in Hallbrook. I didn't find anything, but it was a very exciting experience.
Okay, I was going to ask you if you'd ever participated in a meteorite recovery expedition and what that experience was like. So you've done one. Was there any special training that you had to get in order to prepare for this kind of expedition?
Honestly, no. I have a lot of friends who basically make a living going out there hunting for meteorites and selling them. So it's like a business. They're very good at it. They know very well when they see something, what is it? Because they have had like a long time experience. And because I'm friends with them, they were like, "Oh, why don't you come join us?" So I said, "Yeah." What we did, I took a stick and I taped a magnet at the very bottom of the stick. So I was just kind of using it to swipe around as I was walking in the desert. But it's like you're spending hours out there and it's sunny and you can get sunburn and it's not a lot of fun, especially if you're not finding anything. But if you end up finding something, it's like it makes it all worth it. But usually, next time I go to find meteorites, I'm not just gonna go like on a field where I might find something. It's better to go where you actually know there is a fall, and then you're going specifically to look for that fall because you want to recover samples. For instance, we just had very recent fall in Ohio that
Right.
everybody heard. It made like a sonic sound, like shockwave. And I had all my friends flying to Ohio to look because they knew exactly where to look and they were finding pieces. So that I really wanted to go to that, but my schedule was such that it didn't allow me. But it was really fun to see people that they were actually just going there, looking around and finding samples. And that was like really fresh, really fresh.
Wow, pristine samples,
Yeah.
pristine samples, wonderful. So now, we can see the lab behind you, and you've already mentioned a scanning electron microscope. So I'm curious to know what are the main tools and instruments besides the scanning electron microscope that you use to analyze your meteorites and to actually confirm first that the rock is actually a space rock, and then what other tools do you use for your research?
Yeah, so the classification for meteorites, that's not what we do here, although we could because we have the tools, but nobody in our department actually receives samples just to classify whether this is a meteorite or not. There are groups and research facilities in New Mexico, in Portland University, that they actually just do that. They classify samples. What we do here is mostly we know what a meteorite is, and we get very thin slices of these meteorites, and we use a scanning electron microscope to actually study the features, the texture of the meteorite sample. So we look into chondrules. So if you have a meteorite, a specific type of meteorite that formed like the first types that formed in the early solar nebula, it will have these tiny circles that we call chondrules. It's a type of um, material that actually formed under very, very high temperature. So
Yeah.
these spherules are like in the meteorite, but the matrix, like the cement that keeps them together, it's kind of fine grained material that formed under not so hot temperatures, which is kind of funny, right? You have two different materials that formed under different conditions and still ended up in the same rock. So
Yeah.
that's what we actually use the scanning electron microscope to see what the composition of the chondrule is, what the composition of the rim of the chondrule is, what the composition of the matrices is, and then trying to piece together, okay, we have these chondrules that formed here, and then you're having like this fine material that might have formed here at like this distance from the sun. So kind of trying to piece together what happened in the very early solar nebula when everything was just dust and gas. Um, but yeah, the classification, basically they also use scanning electron microscopes. I have very good friends who do that. But yeah, we don't do that here, but we do a lot of cool science here with meteorites, all kinds of.
Well, let's get into the cool science that you do with the meteorites. So, but we can see part of the lab behind us. Can you take
Yeah.
us through and show us the sites of your lab, and maybe perhaps even see something under the scanning electron microscope, if that's possible?
Yeah, electron scanning microscope is not in this room. We will get to
Ah,
it. I can go in the other room, but I will just start off showing a little bit of my space. I also have a camera in the back of my computer, so I'll just rotate it. But
wow.
basically, what I do, I actually study asteroids and I study organics on asteroids. So what I'm trying to use is like fragments of asteroids to understand the organics there through spectroscopy. So basically, I take meteorites, I powder them down, and then I add organic content to them. And then I take the spectra to try to see how I can match that spectra to what spectra we're seeing out there in the main belt. Um, so the device that I use to take the spectra, it's called the Fourier transform spectrometer. It's an FTIR. We do not have one of those in the lab, so for that I actually have to go to Stanford to use in their lab. But I'm just gonna show you the area where I actually prep my samples, right? This is my desk where I basically measure. This is a measurement where I put my powders of the meteorites in these tiny cups, and I usually put it in there. It has like a window that opens on the side like this, and I can place it there, and then it tells me how many milligrams do I need from the meteorite. And then these here are all the different ammoniated salts that I use to mix my meteorite powder. You can see ammonium acetate, ammonium chloride, formate, different ones, because this is what we want to see whether these ammonium salts are actually present in the asteroids that we see out there. So that's why I want to add a little bit of this to my meteorite. And then when I take the spectra, I want to compare that spectra, whether it looks to what we see um, in with the telescopes, basically. But once I do that, I also have to bake my sample because we don't want any water whatsoever in our sample. So we have to remove all the water. And for that, we actually use this oven, which is a vacuum oven. When you turn it on like this, you can set the temperature. I normally will do like 120 or 50 degrees Celsius, depending on my samples. And then once we set the temperature, we can just turn the vacuum. So like all the space, everything that is inside there, it's going to be baked under vacuum. And then I grab these samples, which actually look like this. These are all my samples that I have used over the last 2 years. You can see how they look like. So you see these fine powders. They're all like mixed with different percentages of ammoniated salts. Like this is a little bit of meteorite. See that? It's all fine powder. And then, yeah, I take them like this and I just put them in here and they will bake for like a week. And then I take them out, I put them in a container, and then I drive to Stanford where I actually measure the spectra, which is pretty cool.
Yes. Okay, so did you say that you put the sample in the oven for a week?
Yeah, that's correct. Because I want all the water to be removed from the sample to like bake out and evaporates, and then the vacuum will keep it very pristine. And then I have some containers, which I cannot find them here right now, but they're like tiny containers that I put my samples, I close the cap, and then I vacuum out all the air so that the sample it's not going to collect water from the atmosphere. Like in here, like we have water in the atmosphere, and although we don't feel it, if you put it under the FTIR, you can actually see that water has been absorbed back. So I try to keep my sample as pristine as I can until I drive to Stanford and I open it up and I measure it. But yeah, this is a desiccator where we keep all kinds of different meteorite samples. We keep them in here because we want to make sure that they're like dry and not like just in ambient room conditions. So when something is dry, then it will not be able to oxidize and all of that. These are very precious samples, very expensive samples too. And yeah, this is not just what I use, it's also what my friends use. Like we have ordinary chondrites, we have carbonaceous chondrites, we have like murchisons and some very, very famous samples that are very much known to have been used to science. And we have learned a lot about the solar system through these samples. So yeah, this is parts of the lab. And then we have actually outside, I'll turn the camera, we have like this area where we actually just use to prep the samples, to grind the samples. This is another oven that we have. It's not a vacuum oven, it's just a regular oven where we need to like heat something up or stuff like that. Another scale, and then these are all different, what do you call them? Gratings? Ah,
that you
yes.
use. Yeah. So there's like classes that are on petrology and other things that we use all this material for. These are also other desiccators that we keep samples, like for instance, this one. So the air is being sucked out of this. So it's keeping the environment inside very dry. It must be somebody's samples in there. I don't know, not
Yeah.
mine. And yeah, you can see like we have more samples here that students are working on different classes. This is where we have the sieves. These are the sieves that I use. You can notice here in the side, for instance, this is 20 micron. So if I want to have 20 micron grain sizes for my meteorites, I grind it up and then I sieve it with this. And this only allows to go through whatever is like 20 micron and less. So I use these sieves a lot, by the way. We have
Yeah.
different ones. And then it's this other section of the lab. So we just saw that in the room there with the oven that I use. We have this area here. It's this device that I myself have never used, and I'm not quite exactly sure how to explain it other than when we have a sample, a slice of meteorite, before we actually put it in the SEM, we have to put it here and add a layer of like charged particles, I think. And then we have to put it under the SEM. So I've never used this personally, but it's nice that we have it. We have
What do the charged particles do? Why is that layer added?
because we are basically shooting electrons into the samples. So I'm not quite sure why, honestly, we need that layer of particles, but I just know that's what this thing does. And if you have a sample that you need to analyze under SEM, you have to do this beforehand and then put it under the SEM.
I see.
Yeah.
I see. Yeah.
And then we have this microscope, which is actually a really nice microscope. It has like binoviewers, it has a single view, and it also has the area where you can put a DSLR camera and take really, really pretty pictures of meteorite slices. It has different magnification. So it's basically a really powerful microscope. We use this one usually to just check out the texture, the mineralogy of our samples. Instead, maybe if I turn this on, you can probably see a pretty picture. See that pretty picture? Like that's
Oh,
what a meteorite chondrule looks like. So this could be like maybe, I don't know, less than 10 micron across. Like these are very, very tiny, but yeah, it looks really pretty when you
it
take a picture like that.
oh, that's incredible. So you said regular classes come in and use this lab as a part of
Yeah,
their normal well, I guess it'll be a lab segment that goes along with like a
that
petrology
is
class,
correct.
for
Yep.
example.
Metrology class, because my advisor Miriam, she actually teaches different classes. She also has a cosmochemistry class that she offers sometimes in the fall, and where we study meteorites. So actually, students of that class, I took that class when I first on my first year of PhD. So we were like 20 of us who came in here and learned how to get a sample ready to study with SEM, how to grind it, how to polish it, how to take standards, to use all of these different gratings. And it was very, very interesting. So yeah, this is the purpose for the lab. And then we also have grad students who are working on different projects. Like for instance, my colleague Jill, she studies chondrules, especially the rims of the chondrules. I study the organics on meteorites, so I don't need to look at a pretty sample. I'll just crush it down, make it a powder, and that's what helps me. And then I have my other colleague who actually melts the meteorite with this device that is right here. So this device allows you to actually put a meteorite, melt it, and all the gases that are being released, that's what you study to understand the atmospheres of exoplanets and compare
Whoa!
it. Yes, it's crazy. Like all of us study meteorites, but in a different way to understand different things. So yeah, I like this one. I've never used it myself, but my colleague Nathan uses this device to try to understand these volatiles that being evaporated or like released, all the gases when you melt a meteorite, and then you compare that with the spectra that you get from atmospheres of exoplanets and see how do they relate and whether we are having the same type of material.
That's incredible. That is absolutely incredible. Thank you so much for for this tour. So, let's say you've gone to Stanford and you've done the analysis that you need there, and now you're back in your lab. What's the next step?
Um, so basically the next step is I take that data and I look at all those samples, all the spectra that I have taken at Stanford, and I will look for different absorption features. So I look for very specific absorption features in the 3 micron region because that's where you can actually detect salts, ammonium salts, and soluble organics, and so on. And then I compare those features. Like, do I see the same features that I see with NASA's telescope that I use in Hawaii? I use IRTF to look at hydrated asteroids. And then they have very specific features. So when I do this in the lab, I try to match those features. Like, are they matching? If not, why they are not matching? Do I need to add more of this compound to make it match? So basically just trying to kind of fit in the spectra. And it's really fun because it's also a little bit challenging. You're trying to compare something in the lab or to make like an asteroid-like condition in the lab. Um, and then check out like the spectra from like so far away that we take out there in the main belt. But I really enjoy doing this. It's really much fun. So yeah, it's my pleasure to be here and show you around.
I do have a few more questions. So, you were talking about the collaboration you have with Stanford. How did those come about, and do you have those kinds of relationships with other facilities that helps you with your research?
Well, the collaboration with Stanford was basically the fact that we do not have the equipment that I really needed to conduct my experiment for that research project. So we reached out to them and they definitely, we're more than welcome there. That's not the only tool that we use. We also use their EPMA, which is electron microprobe, which is a little bit different than the SEM. We don't have that one either. So my colleagues can go there and utilize their labs, which is actually a really great form of collaboration because it allows us to conduct research using their tools. So yeah, the FTIR is in their lab. It's also quite convenient for me because I live in San Jose, so it's a lot closer. But yeah, it's like my advisor basically reached out. My advisor has very, very good collaborations with Stanford. So I'm very lucky that I get to kind of work with both universities, honestly.
Meteorites can tell us so much about the formation of the early solar system. Is there one or two things in particular that you have discovered, you and your colleagues have discovered from with your research that has given you some new insights into the solar system formation?
Well, yeah, for my research in particular, we were looking at these group of asteroids that are called sharp types. They're showing one specific absorption feature, and then the other one, it's not sharp types that shows a different specific absorption features. But if you look at them in the visible region, they all look alike. They all look the same thing. So they're both hydrated, but there's this specific feature that it's making one a little bit more different than the other. So that's where I wanted to understand what is making this other group in the infrared a little bit different than the other. So that's where I actually took different meteorites that matched this group, and I was using ammoniated salts to try to add it to make this one look more like the other group, whether I can actually shift the spectra. And when I did that, I came about that soluble organics, because we have organics that are insoluble also, but specifically soluble organics, ammonium formate, ammonium acetate, we're actually shifting that spectra and making a meteorite that looks like this group look more like this group. And that kind of tells us that, okay, maybe this is what is out there in the surface of these bodies that it's making this look like this. But then also the question is, how do we have that in the surface of these? Like, how did these organics end up being in the surface there? So that's what I'm currently working on, a second project to try to understand, like, how did fluid mobility, maybe transport or redistribute the organics in the early planetesimals when water was convecting and moving things around. Maybe that's what was happening in these asteroids. And that's basically what I'm trying to find out as I'm working on this project.
Oh, so when you talk about organics, I know we have lots of different ideas about what organics mean. For you specifically, and for your research, what are organics?
So, organics are basically, they can be different. It can be amino acids, it could be carboxylic group, it could be amines, it could be alcohols, like literally like different groups. And also, people are interested in organics because we have life on Earth, but did life just form on Earth, or did it actually come from elsewhere, from like comets and asteroids that formed much outer in the solar system where organics were more present? They accreted all those organics, and then maybe they actually fell here on Earth and brought the seeds of life. So when you study organics, it's very exciting because you're literally studying something that could potentially mean life. But in my case, I actually I'm very specific only with the carboxylic groups, which are like salts. I don't even do acids because trying to like mix meteorites with acids in the lab, it's just very not very practical. Let's put it that way. So I just utilize the salt forms, which are like ammoniated salts, because also we kind of know that a lot of these asteroids did not form where they are today. They actually formed much further out in the solar system beyond the ammonia snow line. So they accreted a lot of organics and ammonia, and then they actually traveled inwards. um, so in some way, for me, it's kind of nice to understand how these organics are actually surviving on these asteroids, how they are being preserved. And maybe this could even help someone else to understand how are the organics being preserved and like brought back to Earth, and how did life form? Like how did everything start? So kind of feels nice to be kind of part of that big picture, sort of big puzzle.
Yes, absolutely. I mean, this is the cutting edge research helping humanity understand our place in the universe and how we even came to have a place in the universe, Fran. This is an incredible tour of your lab. It's very exciting to start to get some insights into the research that you're doing. And to wrap things up, I'm sure there are plenty of people who find this field of study as fascinating as I do. So, what advice would you give to students who are interested in pursuing a career in planetary science in general, but in meteorite research specifically?
Uh, yeah, honestly, I know a lot of younger people who love astronomy in general or planetary science, but meteorites are a lot of fun because you're getting to work with material that it's older than Earth itself. That alone, it's kind of like mind blowing. It's
It's
really
mind blowing.
interesting, and you're trying to answer questions that are 4.5 billion years old, trying to piece together the blueprints of our solar system. And it's like, to me, that's the most fascinating thing. And if you really love that, you can make it happen. Especially like if you're a student here in the United States, you have so many opportunities. I come from Kosovo, so for me, it was quite challenging to have to actually leave my country and move here and like chase my dreams. But here I am doing exactly what I love. So what's stopping you, right? I'm very sure that anyone who really is very determined, very passionate about what they want, very curious, you can literally reach anything you want, and no one can stop you but yourself. So keep that in mind. Before we end our session, though, I also brought some meteorites, my personal collection from home that I would just like to show like a few samples that I have.
Yes.
Um, I will start, I'll start with this. If that's okay, good.
Yes. Oh, wow.
This is actually a Sikot Allen. It's a completely metallic meteorite. It's iron and it is heavy and extremely magnetic. I don't have a magnet here, but actually I do, it looks like. This magnet.
Oh,
Yeah, it's pretty cool. I actually got this one in the flea market place, believe it or not. But it's nice. This actually fell in Russia. It's a very famous meteorite, Sikhote Allen. And I read about it. It's like when this fell, it was like fire falling from the sky because it just dissolved in all these pieces. Like it's like fire falling from the sky, like the biggest meteor shower witnessed in 1947. So I really like it. Look at those like melted features as it's
Yeah.
falling. It's very sharp. Sometimes I use this to open Amazon boxes too. Yeah.
Wow. And you
And
said
my
you found it, you bought it at a flea market? Did they know what it was?
They did know, but they didn't really have a lot of information about it in terms of like the value and so on. So they sold it to me for a very reasonable price, and of course, I got it. But yeah, I'm very happy that I have it. It's a very famous meteorite. It's not very cheap, so I kind of got a good deal out of it. I was very lucky. Right place, right time.
Yes.
My other one, it's also an iron nickel meteorite. So, by the way, these come from the core of asteroids. So, when a planetesimal has grown large enough and it has been able to melt, when you melt material, the heavy material elements will actually gravitate towards the center. So, all the iron and nickel and heavy material will actually go and kind of concentrate in the center, and then in the mantle, you will have all these crystals that form. Like the olivine crystals are like the first to crystallize as the temperatures are cooling down. So they will go all the way sink to the bottom of the mantle, to like the core mantle boundary. And then you will have the crust that it's still processed material, but it's mostly like light elements, silicates, and maybe rare earth elements. So this is another sample that is an iron meteorite from the core of an early differentiated planetesimal. This is a Campo de Cielo. It's a famous meteorite that fell in Argentina. It's so bulky that you will find the piece of this meteorite basically in almost every gift store of a science center around the world because it's very bulky and it's being distributed worldwide. I hear that it's illegal now to distribute this outside of Argentina, based on their new regulations. But I also bought this was like a big chunk. They just took a slice of it, so you can see these really, really cool features that has to do with the temperatures of how they cooled in the interior of the planetesimal. So they didn't polish the side, they only polished this side so you can see the cool features here. But it's also very sharp and very, very magnetic, as you can imagine. I just got last weekend a very special sample. I couldn't resist, but I bought it. This is the famous Canyon Diablo from the crater in Arizona, the big meteor crater that we have there, the Behringer crater. Uh, it's also metallic, very heavy. You can, it's really heavy, but it's a little bit rusted. It's been oxidized, but it's a very nice chunk. I was at an astronomy conference in New York and I couldn't resist because this was like one of the famous ones I didn't have, and I have to have it, of course.
Of course.
And another one that I really like is this one here. This is
Oh,
actually a piece of the moon. It's a lunar meteorite.
that's a lunar meteorite.
So basically, when an object hit the moon and all the debris that got scattered, and we're talking about a big impact, something that can
Yes.
escape the moon,
Yes.
came and fell all the way into Earth. So basically, this is lunar material that escaped from a big impact from the moon and came and fell on Earth. It's like a breccia, which is melted material, like different clumps that then kind of rejoined together. I really like this piece. I normally don't take it outside the box. It's very precious. It's very thin slice, but I'm very happy that I get it. And usually when I go to schools and I do outreach and I hand this to students, like, hey, you're holding a piece of the moon. It's quite exciting. And this is a piece of Mars. In a similar way, this came from Mars. I don't know if the camera is doing justice, but this is
Yeah,
also another one that I prefer not to open and take it out
of
of the box.
course.
Because once you touch these samples, like all the finger oils and everything can make it not last so long. And for the another sample I wanted to just kind of show quickly is like just a regular ordinary chondrite meteorite. This is like one meteorite that kind of makes up the most abundant type that we have here on Earth that falls here. It's ordinary chondrites. But the reason why I want to show it is just because this black outer layer is called fusion crust. So when this meteorite is entering the atmosphere, it's basically burning. So all the burn, it's basically this layer. So if you cut this in half, it's not going to have this layer inside. It's going to look very different inside. But it's I have slices of this meteorite. They have very nice chondrules, but this one I wanted to show just because it's just like one piece meteorite and it has a very beautiful fusion crust. And for the last, I wanted to show this one, which is basically my favorite that I have. Probably you know when you see it. It's a Chelabinsk meteorite.
Chelyabinsk. Wow.
Yeah, so Chelyabinsk, for all of those who don't know, was a 20-meter object that actually fell over Chelyabinsk city in Russia. And when it fell, it exploded midair and created a shock wave that basically broke windows, injured 1,400 people. And can you imagine? That was just 20 meters. And it was a rocky asteroid. Like, imagine if it was metallic, it would have been probably 3 times the damage. Um, but yeah, and the glass that you see here is actually glass that was broken by the shock wave of this meteorite. So this broke midair, and then all the samples fell down. The main mass fell on a lake, which is the size of a table, which was recovered, by the way. But yeah, I have these 3 tiny samples that were given to me by my friend Topher, who's a meteorite collector from Arizona. And I really like it because I remember I was in Kosovo and it was 2013 when we were watching the evening news and they were like, a meteorite fell over Russia and injured and injured people and made all this damage. And I was like, no. And I think until that moment, people don't realize that these things can be dangerous for for life on Earth. And yeah, it's good that we keep eyes on the sky and we're good. Nothing is headed towards us. But yeah, this was kind of like a wake up call for the planetary defense and everybody else. And I'm very happy that I own this because it kind of fell in my lifetime. And I don't know, I have a special connection to this meteorite. Anyway, these were just a few samples that I just wanted to show. I know it's kind of hard to see through the camera, but I do have a lot of meteorites that were given to me over time, donated to me from different um, collectors because I do a lot of outreach with schools, and it's always a pleasure to go out there and hand someone some space material they can actually hold and learn about it, especially children. So yeah, it's been a pleasure to share this with you. Thank you.